When you look at a modern smartphone, you see glowing glass and sleek metal. But if you strip away the polish, you are basically looking at a highly organized pile of rocks and minerals, which raises a pretty big question. How do we trick completely lifeless materials into playing video games, storing our photos, and running applications? To understand that, it helps to think of electricity as water. Imagine a steady stream of water flowing smoothly through a system of pipes. If we want to build a device that can actually process information, we have to find a way to precisely control and steer that flow of electrical water. In the world of electricity, most materials fall into one of two extremes. First, we have materials that act like a wide open pipe. We call these conductors, and they are essentially a green light for electricity. Look at this simple circuit. Copper and gold let electricity flow through them with almost zero resistance, which is exactly why the insides of the wires in your house are made of metal. On the other end, some materials act like a solid, impenetrable wall. We call these insulators, the red light. If that metal bridge is swapped for a block of glass, the flow stops completely. Glass and rubber block electricity, keeping you from getting shocked. But here's the problem. If we only had materials that were permanently stuck on go or permanently stuck on stop, we could never actively direct the electricity. We wouldn't be able to do math or run programs. This is where a very special type of material comes in. It sits exactly in the middle of our two extremes. We call it a semiconductor. If a conductor is a green light and an insulator is a red light, a semiconductor is the traffic light of electricity. Under normal room temperature conditions, it might act like glass and block the current entirely. But if we change its environment just a little bit, it suddenly acts like copper and lets the electricity pass right through. This gives us control. Because it can switch back and forth based on its environment, it is the perfect material to build an electronic brain. So how do we actually switch that traffic light from red to green? It turns out we can push a semiconductor to conduct electricity by adding a little heat, shining a light on it, or applying an electric field. By doing that, we create a digital switch. We can turn the flow of electricity on and off entirely on command, without a single moving part. Look at these early physical electronic components. They relied on thick metal wires, glass tubes, and bulky casings to control electricity, which meant they were slow, fragile, and took up a huge amount of space. Because a semiconductor switch has zero moving parts to wear out, it can switch on and off at lightning speeds without ever breaking. You might think a material with this kind of ability is incredibly rare, but the most famous semiconductor on Earth is actually right under your feet at the beach, silicon, which comes from ordinary sand. Silicon is highly stable and handles intense heat beautifully, making it the undisputed king of the modern microchip. But scientists also use other materials for highly specific tasks. If you look at the geometric panels covering this spherical satellite, they use a material called gallium arsenide, which is perfect for capturing light in the extreme environment of space. There is also gallium nitride, which manages high amounts of power while staying cool. That is the exact material used inside modern, ultra-fast phone chargers. Whether it is silicon in your computer or gallium arsenide in orbit, the core concept remains the same. By picking the right material, we can put these tiny traffic lights into almost any environment. Now, a single microscopic switch turning on and off isn't very smart on its own. To build a true mechanical brain, you need millions of them working together. Instead of building them one by one, engineers use highly focused light to print massive, complex circuits of these switches directly onto a single flat piece of silicon. If you peer into the center window of this microchip, you can see tiny, hair-like wire connections bridging the gap to an incredibly dense grid. Millions of microscopic switches are packed into an area the size of your fingernail. When you link millions of these tiny switches together and flip them on and off billions of times every single second, that piece of silicon can execute complex math, store memories, and run the software you use every day. Semiconductors serve as the vital brain cells of our modern devices. Look at the sheer size of the mainframe computer cabinets dwarfing the engineer sitting at this desk. Before we mastered microchips, computing required rooms full of massive equipment. Today, all of that logic is handled by materials that sit perfectly in the middle. They aren't totally open, and they aren't totally closed. They just wait for our commands. Without our ability to carefully control these highly specific materials, the global internet, modern medicine, and the digital devices we rely on simply would not exist.